About measures of center and which one to use in different settings, let's move on to measures of spread or variability in the data. The first one we're going to talk about is the range. This is the simplest measure of spread, and just think of it as the difference or the distance between the largest data point and the smallest data point. This little sign here literally means subtraction, so make sure you're subtracting and not writing down two numbers. The range is one single number, the distance between the smallest and largest observations. So consider our kind of corny examples we have going on here with the kids sitting on the seesaw. We had them at 3, 4, 5, 6, and 7 feet. So our range in this first example is going to just be the difference between the largest data point and the smallest data point, or a distance of 4 feet covered by the data set. This second data set, same idea. We had this observation, little Johnny moved way down to the end of the seesaw at 17 feet. All the other data points stayed the same. So we have 17 minus 3, or 14 feet. So two data sets nearly identical except for the last observation. So based on our definition of resistant, is the range considered a resistant measure of spread? Probably a big no here. By changing the last observation, our answer changed greatly. In fact, our definition for range is defined by the extreme observations. So of course, it's not going to be resistant to change in the extreme observations. So even though the range is very simple, usually we're not going to use this measure of spread. The next measure of spread we're going to look at, some of you may have heard of before, it's our standard deviation. Make sure you know the interpretation of this. It's telling us the typical or average distance of observations from the mean. So we'll use that definition to take a look at finding the standard deviation for a data set by hand. So let's use our original data set here, the 3, 4, 5, 6, and 7 feet. I'm going to draw our picture as a reminder. We've got our observations at 3, 4, 5, 6, and 7 feet. And if you remember for this example, the mean is our balance point all the time, and we could easily see, well, the mean then would be here at 5 feet. So x bar, the mean of the data, is at 5 feet. And let's check out our definition again. We're looking at the average distance of observations from the mean. So first, before we can calculate it as an average, we need to find all the distances. So I could just look at this and say, okay, 6 is 1 away from 5. 7 is 2 away from the mean of 5. And then on the other hand, we've got 4 is 1 below the mean of 5. 3 is 2 below the mean of 5. And then we also don't want to forget, 5 is one of our observations too, and it's 0 away from the mean. It is the mean. So this is kind of a picture to help us see what we're measuring, these distances of points to the mean, the balance point of the data. Let's maybe draw this as a table. I'm going to label this as step 1. So I might write this as x, a data point, and I'm seeing how far it is from the mean. That's what we're doing. We're subtracting to find that distance. So I've got the data points 3, 4, 5, 6, and 7. And I've got the mean is 5, so I'm subtracting to find the distance of each data point to the mean. And we saw earlier that gave us 2 below, 1 below. 5 is the mean itself, so that distance is 0, 1 above, and 2 above. Now, if you look at our definition again, we're basing this off. We found the distance of observations from the mean. We just found that. Now we need to make it into a typical or average distance. So if you think about average, that means add up everything you have, divide by how many there are. So if I add this up, we should get, you'll notice, all of these cancel out to a distance of 0 feet. Okay, great news. That means we did this right. We would get 0 feet every single time. Maybe make a little note to yourself. I'm running out of room here, but 0 feet happens every time. And remember, that's because x bar, or the mean, is the balance point of the data. So it literally balances the distances below it with the distances above it. So balance point, we expect this to add up to 0 because it's balancing distances of data points below and above that mean. All right, so since we get 0 every time, to find an average, if we add it up and get 0 every time, that's not really going to be informative and helpful. So we need to do something to get something a little more informative here. We could take the absolute value of this. So we're just kind of ignoring above or below and just look at the raw distances. That is a calculation called absolute deviation. We're not going to do that. We're going to do standard deviation. So our solution here, remember this, you'll see it a lot throughout the semester, is to square those distances. If I square them, it makes them positive. I'm going to label this step 2 here. So find the distances, square them so we get something useful that's not adding up to 0 every time. So 4, 1, 0, 1, and 4. Now if I add all these up, I get 10. And we want to be real careful. These are squared distances. So now my units are 10 feet squared. Now we're getting closer. We've got the squared distances from the mean that don't add up to 0 anymore. So maybe let's look at finding the average squared distance. I'll call this step 3. And the terminology for this calculation is called the variance in the data. So variance is the average squared distance. And we're going to use this notation s squared to remind us it's a squared distance. All right, so the variance is again given by s squared. It's calculated by, remember this sigma means add them all up. So I'm adding up how far the points are from the mean squared. So that's this number down here. That's our 10 feet squared. Just adding up. I've added up all those squared distances. So that's all that notation means. And then to make it an average, we need to divide by how many we have. Now some of you that have seen this before, you know it's not divided by n, how many we have. There's an adjustment. It's divided by n minus 1. There's several reasons for this. The main reason is so it's not a biased estimate of the variance, but you don't need to worry about that in this class. Just know this is almost like an average. Instead of dividing by n, it's n minus 1. So here, our n, we had 5 data points minus 1, and we get 2.5 feet squared. So if we wanted to interpret this, we would say something like the average squared distance of points to the mean is 2.5 feet squared. So average squared distance to the mean. We'll jot that down. So our average squared distance to the mean. Okay. We're almost there with our definition now. We didn't want the squared distance, we just wanted the regular distance. So to undo the square, we're going to take the square root. So that's our last step here. So this is what we're looking for, our standard deviation. And instead of the s squared, we'll just use a plain old s to denote this. So s, to say now we're back in our original units, and really just take the square root of the previous step to undo that squaring of units. Sorry about my pen here. I don't know why this pen tool is acting funny. So s squared. So in our example, the square root of 2.5 feet squared And it should give you 1.5811 feet squared. Okay, and, oh, not squared. Okay, 1.5811 feet. So this tells us the average distance or typical distance of points to the mean. So I'll label that here, average distance to the mean. All right, if you don't have your calculators handy, go ahead and get those for the next video. We're going to take a look at how to find the standard deviation using our calculators, which are free to use for the remainder of the class. But I wanted to do one by hand so you had this notion of how it's measuring spread. You can always remember this picture we have up here, how far the points are from the mean of the data or the balance point of the data. So grab your calculators and let's check out how to use them next.